Hello everyone, my name is Tyler Middlebrooks, and today we're going to be going over Yttrium-90 resin microspheres. These are used for treatment of hepatic metastasis, and today we're going to be doing a size verification. Disclosures: there are no financial disclosures. All the subject matter in this presentation is my opinion. We do use several references and a video from the Sirtex website. They are the manufacturers of these resin microspheres. Topics: what are Sir-Spheres Resin Microspheres? Sphere size, overview of SEM and XPS, our observations and results. What are resin microspheres? We did use Sirtex Resin Microspheres for the evaluation today. Sirtex Sir-Spheres Resin Microspheres are only indicated for the treatment of unresectable metastatic liver tumors for primary colorectal cancers. What you're seeing here in the image is contrast being injected into the liver. You're able to see the hepatic arteries. You're also able to see some tumors there that hold on to the contrast. You kind of see that tumor blush, but a really, really cool image there. There are two portions to this test. There are the mapping and the treatment portion. The mapping is essentially a practice run. We do inject a radioactive particle similar to the spheres, but they're not designed to treat. It's more of a diagnostic or imaging agent. It is considered like a practice run. We're also able to evaluate lung shunt, how much of these spheres or beads are being shunted from the liver and getting out of the liver and going into the lungs. We want to make sure we don't treat the lungs, just the liver itself. We're also able to evaluate catheter placement. We don't want any contrast to reflux back to any other organs in the body. We want everything to stay exactly where we want it. The treatment portion, we do essentially the exact same thing. We inject the Y90 spheres into the liver. We also acquire a post-treatment PET-CT scan for localization and dosimetry evaluation. We do want to know where these spheres located, where did they stop, and what kind of dose is being delivered to the tumor. We do want to ensure that the tumor is being irradiated to a tumoricidal level, which will kill the cancer cells. Why use Yttrium-90? Well, Yttrium-90 has 51 neutrons, 39 protons. It does decay by beta decay to a stable zirconium-90. The half-life is 64.1 hours. The 10 half-lives, 26.7 days. The beta particles only penetrate in human tissue or in tissue about 2.5 millimeters. That is about the size of 2 dimes stacked together. If you look at the image here, a nickel, is that first image, is about 2 millimeters. 2 pennies stacked together, that's about 3. So, but about put two dimes together is about the distance that the beta goes away from these beads. So the majority of all the energy of the radiation is very, very localized. You don't get almost any damage anywhere else in the body, at least that we can see. So all of the energy is deposited extremely close to where the beads end up. If you look to the image to the left, that is an image of a liver. The green is the normal liver. The bright red is where the beads localized. That is a PET-CT image. We're able to evaluate and see where they localized. If you look at the image to the right, that is an axial slice through the abdomen. It's the exact same patient. You can see on the left half of the image, there's no activity, no color. The right side, it's the bright color that shows where the beads are located. Sphere size. Sirtex package insert states that sphere size is between 20 and 60 microns in size. Capillary beds are typically between 5 to 10 microns in size. Some capillaries in the liver can be up to 40, which would allow some of these spheres to pass through the liver and then eventually end up into the lungs. We don't want that. That is another reason why we do the mapping portion. These spheres are optimally sized to occlude or get stuck in the capillary beds throughout the body. I'm sure Sirtex did that by design. Overview of SEM. This right here, if you look to the right, that is a diagram of a scanning electron microscope. An SEM scans a focused electron beam over surface to create an image. The electrons in the beam interact with the sample, producing various signals that can be used to obtain information about the surface topography and composition. We're going to go over the SEM and XPS extremely fast, just real brief here. XPS, X-ray photoelectron spectroscopy, is a surface-sensitive quantitative technique used the photoelectric effect that can identify the elements that exist within a material. If you look to the right, there's another little diagram. The equipment used to the left is an SEM. To the right, that is a XPS. These are the brands that we used. Expected observation. Here are a couple images of what I really expected to see whenever we looked at this sample under the microscope here. If you look, they all relatively look the same. They kind of just look like little balls. They're mostly, seems like they're out of focus slightly, but really not a lot to look at. This image over here on the far right, the one that we brought up here, it almost looks artificial. Not to say that it's not by any means, but there's almost no detail at all, and extremely sharp edges. Kind of looks plasticky. But I'm not sure that 100% that wasn't Photoshop. But again, I have no idea on that. But observation. The image here to the left is at 5,000 times zoom. It is a backscatter image. If you look, there are brighter white spots covering the surface of the sphere. That is the yttrium 90. Those are more dense. If you look at the more smooth or background of that sphere, it looks almost plasticky, kind of wrinkly there. That is resin or carbon. If you look to the image to the right, that's only a 250 times zoom. That again is the backscatter image. This right here really demonstrates the different sphere sizes. Overall, if you look at all the spheres, it looks like they're relatively the exact same size. There are just a couple that are just a little bigger, and just a handful of other ones that are quite a bit bigger. But again, the package insert says that they're around anywhere between 20 to 60 microns in size. That does kind of demonstrate that a little bit. Again, the image to the left is another backscatter image. You can see those denser, brighter spots of yttrium, the smoother carbon resin areas around them. I do believe that the spheres, we had to let these decay down over about 6 months to be completely inactive, and there's no radiation in these samples. But I do believe that leaving these spheres in the sterile water for such a long time it did affect the surface of the resin. At least it kind of gave it that more raisin-like or folded texture there. If you look to the image to the right, that's only 1,000 times zoom. Now that is a secondary electron image. The backscatter, you get that more dense. You can see more of the densities there. This, you do lose a little bit of that, but you are able to magnify in a lot more. Okay, the image to the left is only 100 times zoom. You can really see how small these spheres are. If you look to the right, this is another secondary electron image, zoomed in at 25,000 times magnification. You can really see that yttrium. It almost looks like a sponge or a kind of a lattice or some kind of a crystal-like shape. And then you can see the extremely smooth carbon resin around it. Okay, again, here is on the left, that is the backscatter image. To the right, that's a secondary electron image. You can kind of look at those and compare that the surfaces do look extremely similar, but again, the densities and the colors are slightly off, so you do lose a little bit, but you gain a little bit more magnification there. So image to the left, backscatter, image to the right is the secondary electron image. Again, the same thing. Image to the left is the secondary electron image. Image to the right is the backscatter, but you can really see the difference. Okay, the image to the left here is another secondary electron image. It's only 100 times zoom. This image really demonstrates the different sizes of the spheres and just how many spheres there are in a sample. Look to the image to the right. That's a backscatter, just of a handful there. Again, really high quality image here. Very, very impressed with our equipment. Okay, image to the left is that secondary. That's the one that gives us the added magnification. And you can look, again, that's that spongy yttrium texture. It almost looks like a crystal or some kind of salt, kind of spongy. It's a very, very, very detailed image there. And that is at a 50,000 times zoom on the left. The right is the exact same image, but at 25,000 times. So you really can see right up in there. Image to the left is only 100 times. Image to the right is 1,000 times. Just some more really, really high quality images here. Both of these are the secondary electron images. One to the left is 10,000 times. One to the right is 2,500. Just going to keep going through here. These are, again, amazing images. Very, very impressed with the quality. Okay, results. So this image to the right, what I did is I drew that red circle. I counted every sphere that is inside that circle. I got 26 spheres that were less than 19 microns in size. I got 194 that were 19 microns in size, 4 that were 30 microns, and 2 that were 50. So 86% of the sample is essentially the exact same size. I do believe that after these spheres sat, again, they sat in this sterile water about 6 months to completely decay. That way there was no radiation in this sample when we were testing it. Did affect the size and surface of the spheres themselves. I do believe if we were to get some hot or radioactive spheres, that these things would be just a little bit more inflated. Those surfaces would be really smooth, and it would essentially bump the size of the sphere up very, very slightly, which I believe the package insert says 20 to 60. I believe it would be at least 20, maybe 22, 23, 24. But I'd have to test hot spheres for that. If you look at the image, the circle on the image there in yellow, I did the exact same thing, just a smaller cluster. I only found one sphere that was less than 19 microns in size, 126 that were 19 microns, one that was 30, and one that was 50. Again, that just kind of shows you the distribution of the different sphere sizes. Again, it just by eyeballing, it does look like almost all of them are the same size, which they are essentially, and then there's a couple that are a little bit bigger. Okay, so I took this image here to our right. I did my best and tried to count every single sphere that you could see. Now I got about 2,500, but for this, for our purposes, I'm just going to say that there's somewhere between 2,000 and 3,000 spheres in this one image. The average sphere size is 22 microns. The smallest that I found was 12, but it was partially ruptured and damaged, and I only found one of them that was that size. The largest that I found was 60 microns in size, but a lot of time spent counting tiny spheres. So XPS, the results. This first one is just a background. We'll just kind of glance at this. Look at the chart down at the bottom. Atomic percentages are essentially 0 all the way down, but that is the background. This right here is our first sample. Now, 2% of the sample that we found was yttrium, and about 13% was carbon, and that's about what I expected, because the majority of the sphere is carbon with the yttrium all over the surface. Now our next sample showed pretty much the same thing, but it looks like there's a lot smaller yttrium, so it may just be the sample had less spheres in it. but only about 0.1% of yttrium in that, and then majority of it was carbon. So the binding energy seen with the XPS says that this the yttrium is an oxide. It is a non-metallic. Most likely it's a form of salt. And it is not a simple oxide. So we got to get a little bit of that surface composition there with the XPS. A little more characteristic there. So, okay, thank you, Dr. Watanabe. This was I wouldn't be able to do this without you. This was kind of a very strange class, doing everything virtual, but thank you very much. It was great. I learned a lot. Okay, the last portion, questions and answers. If you have any questions, please let me know. I'll be happy to do my best to answer anything I can. If not, that's it. Thank you, guys.